Alrighty. So yes, I'm going to talk to you today about some work that we've done. So at the Leslie Research Centre we work mainly on adaptation to abiotic stresses in wheat, and it's mainly focused around drought and water limitation as well as frost. So I'll be talking about the water limitation work today, and particularly about stay green. So as Shep was mentioning, we've heard a fair bit about stay green over the years in sorghum, but we're now getting a bit more interested in it in wheat. And it turns out that there's a few differences in wheat from sorghum, and it's also a slightly different story from a story that we've been working on in the past about root traits in wheat. But before I carry on, so I don't forget, I'll acknowledge my collaborators in this work. We've got Matthew Varadier and Corinne Chanou, who've done a lot of the computer work, devising the models and the analysis of the data, and Susan Fletcher, who's done a lot of the statistics for us, and Mandy and Raylene, who've done a lot of the work on the molecular genetics, and of course Greg Harvey, who's done a lot of the experimental work for us. And of course we have a fair bit of help and advice from the sorghum team, including Andy Borrell, who's done a lot of work on stay green in sorghum. So as with sorghum, stay green genotypes in wheat can yield more by staying green longer and photosynthesising for longer and fixing more carbon. We've got a new phenotyping method that can rapidly phenotype hundreds of genotypes in the paddock within a few hours. But the work that we've done shows that we actually need to be phenotyping for both stay green and roots, and this is what I'll discuss with you today, is the fact that we can get stay green even when there's plenty of water around, which suggests that we don't actually, the stay green story is not completely told by knowing what's going on with the roots. So stay green phenotypes, as I say, they stay green longer and yield more, but it's a very interactive with environment, the stay green phenotype, so it can be advantageous, as with sorghum, particularly in underwater limitation. In well-watered conditions, it's often been found to be neutral, but I'll be showing you here today that we can actually find an advantage for it in some of our environments. Not so much in Australia, but overseas, the stay green phenotype's been shown to be disadvantageous, and that's mainly in irrigated environments where there's a lot of water about, and in the growing of rice. So in China with wheat, which is irrigated, for example, they sometimes have to desiccate the wheat to be able to harvest it, and it's just a pain. But we don't see that disadvantageous expression of stay green in any of the work we've done here in Australia. The other thing about stay green is that there's many ways to skin a cat, and you can get a stay green phenotype arising from quite a number of different physiological mechanisms. These are some of the ones that the guys in sorghum have already characterised. You can see that a small canopy size at flowering can reduce water use early, leading to more water after anthesis, increased yield. Then we've got nitrogen uptake and partitioning can be different between genotypes, allowing better nitrogen use, better partitioning, and the leaves to stay green longer. We've found in the past that wheat, we found genotypes that are able to extract more soil moisture from deep in the soil, and that's been important. And it turns out that the genotypes with the stay green also have this characteristic. So the question was, well, is it these roots that are leading to the stay green? And I'm here to tell you that it's not entirely the roots. The roots are important, but they're not all there is. So the other thing about these different underlying mechanisms is that you'd expect, if the mechanism's different, that the dynamics of leaf senescence should be different. And so we decided to investigate this by looking at the dynamics of senescence in a bit of detail. And We started out using a favourable genotype that I've mentioned a bit already, but Cerium 82 is one that yields consistently well in our environments over many seasons. It's shown to be very good in dry years as well as in other years. The phenotype is never deleterious, that we rarely ever see that we're getting less yield because of it. So it's definitely something that's worth chasing. As I say, the phenotype is both stay green, so it's staying greener at anthesis and during grain fill. It's got a narrower root system with more roots at depth than something like Hartog. It's able to extract more water from deep in the soil late in the season when the marginal water use efficiency is very high for grain production. And as I say, this root phenotype and water extraction is important, but we wanted to work out whether there's something else going on for stay green. So I'll show you some results from a population of 184 doubled haploids that we chose from a much larger population. We chose them to be of a similar height and very similar flowering date. And we phenotyped them using the green seeker, handheld green seeker here. You can see Greg Harvey there operating the machine. It allows rapid phenotyping of hundreds of yield plots in the field in an hour or so. So we can go around and do a whole trial in 1 or 2 hours and go around and do all our trials at least once a week, hopefully. We tested them at three sites in 3 years, and the main thing I wanted to point out about the 3 sites is that the one particular site at Gatton in 210 had very high in-crop rainfall, as you'll know. Remember, 210 was very, very wet year, and so it wasn't a water-limited environment. That's what I'm trying to say. The other ones were more characteristic, more typical environments with differing degrees of water limitation. So what we did was we took the NDVI readings and plotted them. So here's the actual numbers that came out of the machine, and an NDVI reading of 0.8 to a 0.9 getting up to 1 is a fully green canopy. Down around here at 1.15 is a golden senesced, completely ready to harvest crop. And we plotted this fitting a logistics curve. That curve that Matthew and Corinne devised fitted the data very nicely and fitted all the plots very nicely. And we could use it to calculate a number of parameters that we were interested in. So we wanted the maximum NDVI for each plot. They're all plotted in thermal time after anthesis. So this is 0 is anthesis for each individual plot. And we measured the time it took for the NDVI to drop down to only 10% of the Nmax, so near the end of anthesis. The time it took, the time from flowering to NDVI 50%, we calculated in thermal time, and to NDVI 90%. We calculated in thermal time. We also estimated from the curve the actual value of NDVI at this 90% time point, at the 50% time point, and that 10% time point, and the rate at which it was declining, the senescence rate. Also calculated a parameter which is the area under this curve, which sort of integrates the effect of all of those things, and it's an overall estimation of the plant's ability to retain greenleaf area. We did that for each plot, as I say, of each trial, and these are the types of variations that we saw. So in some cases we saw differences in Nmax, not always, but sometimes, and so here's one that's actually getting a lower canopy greenness score overall, starting at a lower level than these other 2 genotypes here. and it's declining, you'll see that it gets to its 50% loss of 50% of its NDVI quicker than these other two, and it actually yielded less than them. These two here actually started at a very similar level, so there's not a difference in where they started. But this one here started to decline sooner after anthesis than this one here. So it's declining, and again it's reached its 50% level earlier than that one. So it turns out that in the terms of these three plots, it was that one yielded more than that one, and that follows the stay green as well. Okay, thanks, Shep. So that's the sort of difference that we got. Here I've plotted the correlation between yield and the parameters we just discussed, and you can see particularly in terms of the TFN 90, the start of anthesis, the timing of 50% anthesis, and that integrated character, that we've got strong positive correlations between each one of those and yield at all three of our sites. And the point I'd like to make is that it's not only the normal water-stressed sites, but also at that very wet site at Gatton that we see those strong correlations. So that suggests that it's the stay green, in case of these parameters, is not dependent wholly on roots, because you can get this strong positive correlation even when there's plenty of water about, so it can't be wholly dependent on roots. So the thing is, okay, we can rapidly phenotype these genotypes, and that's fine, but we still have to get them through to the point of doing yield trials, which is, of course, the most expensive part of any breeding program. So we're trying to be able to select for these things prior to having to put all the genotypes in field trials, and while they're still segregating in earlier generations. So we're looking for molecular markers, and this is just a quick map to show you the genetic locations of a number of the QTL for root traits that we've previously identified, but the ones that are circled in green are QTL for root traits which also correspond with QTL for stay green and yield. So this is where the roots and stay green QTL do correspond. But the other point I want to make is this is only a few of the stay green QTL, and we've got a number of other ones that don't correspond with the root QTL. So the take-home message is that we've got independent determinants of the stay green phenotype. Roots are important, but there are other independent determinants. So we need to phenotype for both roots and stay green to get the full expression of the phenotype, to get the full benefit of it to the growers. And we're currently in the process of integrating this material into backgrounds suitable for the breeders, following them using both the phenotyping methods and the genotyping methods to get these phenotypic characteristics and the QTL in the packages for the breeders so that they can get the varieties to the growers. And that's the current project. This work I've showed you here largely results from a couple of projects leading up to our recently started one. So that's it. Thanks, Shep. Thank you very much. That's what I wanted to say. The main effect of stay green is after flowering, so it's extending that green period after flowering. Your grain number's already been set by the time you're starting to see the expression of the differences in stay green. So the higher yield is generally associated with larger grain size. So that is often associated with lower protein levels. However, it has been shown that you can get genotypes with the high yield and retain the high protein. For example, some work that's been done by the CSIRO Plant Industry Group in Brisbane on another population that is in some ways related to this one, called Siribabax, shows that yes, you get a lot of lines with large seed size, large grain size and higher yield but lower protein, but you can pick out a small subset of lines that have both. So they're obviously the ones that we're wanting to look for. In terms of how much nitrogen you need to put on, obviously to get a certain level of yield and a certain level of protein, you just use all the same. You don't have to change your numbers, but it's the same sum. You know, if you're expecting to get X tonnes with X percent, that's how much protein you need. That's how much nitrogen you need. And again, with the nitrogen story, if you've got more roots down deep in the soil, if there's nitrogen build up down there from previous crops or whatever, you could get better recovery that way. And so with deep placement of phosphorus, for example, the deep root characteristic, you would anticipate that it's advantageous, but we've not actually done any hard work to try and prove that.